Okay, hello y'all. This is gonna be a quick review for the extended test. For those of you who need it, what we will cover in this entire video will be the few units that we have covered, specifically being numbers, um, ratios, and percentages, algebra, specifically quadratics, and trig, finally chord geometry. Now, if at any point you don't remember some of these, or there's things that you're specifically not understanding, or similar things like that, you can probably check out either my previous documents. Probably you have access to that if you're already looking at this, or maybe some of the school materials, which are obviously always useful. Alternatively, you could also ask AI, but use it sparingly. Don't ask too much, otherwise you will just be learning passively instead of actively, and that's not what we want. Which is also why I will probably have some questions in here at the end of every sort of part, so that you can check if you are actually understanding or are aware of these facts. And obviously this entire video is done impromptu. I'm currently in my room, and so there's nothing planned here. I'll just try my best to get through everything possible in this entire video, and it will probably be quite long, but I'm also trying to take my time for this. So first of all, we have our numbers. Okay. In the numbers unit, we learned about different types of numbers. We learned about sizes of numbers. Specifically, we also learned about scientific notation, significant figures, and similar things. So let's first talk about numbers in general. So the numbers we all know is called real numbers, defined as this weird bold-looking R, and they're called real numbers. Or in Chinese, you would call them 实数. Now, real numbers are basically every single number we know, whether they are irrational, whether they are fractions, whether they are integers, any number that we know. Okay, and this is obviously including, for example, we have 1 is obviously a real number, 2 is obviously a real number, right? 3.4 is a real number, okay? 6.7 is a real number, okay? 34 over 8 is also a real number. Pi is a real number, E is a real number. You get the idea. Every single number that we have learned so far is a real number. Every single number that we have used in math so far is a real number. So that's the biggest set we have, the real set. Okay, within that set, we have what we call rational numbers. Okay, and that's a bold Q. And the rational numbers are the numbers that you can express using a fraction. So, for example, we have 4.8 is a rational number. Why? Because this can be expressed as 48 over 10. Okay. We also have, obviously, something like 3 over 4. Something like 4 over 3 is also a rational number. Okay, and rational numbers actually also include repeated decimals. So we have 4.89, and the 8 and 9 are repeated. So we have 4.898989. This is actually a rational number, which I'll cover why later. So the rational number set is within the real number set. Okay, within the rational number set, we have whole numbers, integers, natural numbers, and depending on how you define it, there's actually an interesting mix of whole and natural, so we will not really talk about that. But within rational, so within the rational set, we outside of the rational set, we have the irrational set, which I don't believe there is a explanation, in letter for that, but that's irrational. Those are the irrational numbers. Within the rational numbers, we have, obviously, the most commonly used type of numbers, the integers, and this is denoted by z. And the reason why we use z is actually because of a German word, which I forgot what it was, but z is German for natural, for integers. So integers are any numbers we use in normal life, we have 1, we have 2, we have -1, we have -3. Any of those numbers that are a sort of, you can have how many ones, right? That's an integer. And so within our integers, we have, in our school, we define the whole numbers. I think that was W. Okay, we define the whole numbers as 0, 1, 2, and all the way through. And we define the natural numbers n as 1, 2, 3, all the way through. And the interesting thing here, that's a W, by the way. The interesting thing here is that typically we actually don't use W and N because of how uncommon we sort of use words for these numbers, right? Typically, even in some British curriculums, you might swap the N and W. In some American curriculums, you might also swap the N and W. Sometimes whole numbers are 1 through infinite, and sometimes whole numbers are 0 through infinity. So we're never sure what whole numbers and natural numbers are. For the sake of simplicity, I actually typically don't even write those. You can write Z plus, right? That's just 1, 2, because 0 is not a positive number. That's just 1, 2 through infinity. And Z plus union 0, right? If you know set notation, which we've previously learned, is just 0, 1, 2 through infinity. So preferably use these two notations instead of the big ones, but if you ever see them in the test, remember our school likes to define them like this. And then, so since we have our things, now we have obviously the reals, the rationals, the integers, and according to our school, inside that we have the wholes and the naturals. Okay? And so that makes up about all we have taught here. Outside this, if you know, there's the complex numbers, but I wouldn't want to explain them here, so these are just the things that we will be talking about. And now on to the question of why repeated decimals are real numbers. So we'll take a quick look at that. This should be covered already. But before that, let's talk a bit about set notation. So a set is defined as a sort of group of letters, a group of numbers, okay, or a group of objects. And within a set, we cannot have repeated elements. So if we had the set 1, 2, 2, 3, the set, in theory, would just be the same as the set 1, 2, 3. Because the 2 is counted twice, we don't really count things twice in sets. We're just saying it's a group of objects. So this set is structurally and in math identical to the other one. And that's the notion of a set, right? It's just a group of numbers, letters, symbols, whatever. All the things we just said are sets that have infinite elements. The reals, the integers, the rationals, these are all sets, right? And in set theory, we have the union symbol, the intersection symbol. The union symbol is the total of the two sets. So in this thing, the union of these two would just be this entire thing. And the intersection symbol is obviously the intersection of the two sets. So that will be the intersect of A and B. So this would be A union B. If this set were A, this set were B, and this would be A union B, A intersection B, if this was A and this was B. And we have our universal set, which depending on the situation, you would write either as a bold U or sometimes as a weird symbol. There's a lot of weird symbols. Some of them I've actually barely seen, but there's a lot of different ways to denote the universal set. So just be careful on how you denote that or how you see people denote that. Typically, just use a bold U. If there's some other weird symbol, it's probably the universal set, right? And then rare notations include prime and slash. And prime is obviously not, so we read this as a not, or a prime. Basically, that means in a, outside of A, but in the universal set. So this area here, if this were A, this outside area, this would all be in A prime, A not, okay? And a slash B would just be a subtracting B, and this is a much more rare sort of thing because, well, it's really hard to define the subtraction operation. But if you ever see this and this in here, right, say that's A and that's B, A slash B would just be this area. Okay. So that's just the basics of set notation that we have not covered. Now we can move on to why a repeated decimal is in fact a rational number. So let's say we have let's start with something really simple, right? We can actually prove that 0.1 repeated, this thing, is equivalent to 1 over 9. And the proof of this is actually really simple. All we do is we multiply. We'll show that we can multiply both sides by something to manipulate this into showing it's 1 over 9. So let's say we have 0.1 repeated. We have no clue what this is in fraction form, or if it's not a fraction, we'll find out, right? And we can say this is s. That should be fair. Multiplying both sides by 10, we have 10s is equal to 0.1 repeated, yeah? 1.1 repeated, so 1.1 repeated. And so we have 1.1 repeated is equal to 10s. Subtracting these two, we have 9s is equal to 1. Hence, s is equal to 1 over 9. If you can't follow along, you can go back. You can understand that. Okay. And so in a similar fashion, we can obviously get other things, such as the very famous or infamous 0.9 repeated is equal to 1 argument, where we let 0.9 repeated equal to s, and then we have 10s is equal to 9.9 repeated. Subtracting these two, 9 is equal to 9s, and s is equal to 1. So 0.9 repeated is actually equal to 1. People say it's approaching 1, but if we have infinite 9s, mathematically, it's equal to 1. And similarly, we can prove, obviously, similarly but differently, we can prove 0.01 is actually a fraction too. So if we let this be s and we multiply both sides by 100, we get 1.11, right? This one is continuing to be repeated, right? 1, etc. That is equal to 100s. And if we subtract these two, we have 99s, right? 99s is equal to, let's see, what is 99s equal to? It's equal to, 0.01 repeated. If we're multiplying that by 100, that's equal to 1.1 repeated, right? And, right, so we have 99s. Subtracting these two, we have 99s is equal to 1.1. And then dividing this over, we have, wait, no, that doesn't make sense. 1 second. I told you this was impromptu. I was not prepared for this to happen. 0.01 is equal to... okay, sorry. We'll look at 0.01 later. 0.01, this 0.01, okay. This 0.01 is basically just 0.1 divided by 10, right? 1 repeated divided by 10, which is just equal to 1 over 90. Okay, that one should be a bit obvious. What I was talking about is this 0.01, where these two are repeated. So that looks like 0.010101, etc. This number, let's let this number be s this time, okay? Multiplying both sides by 100, we have 1, right? Notice 0.1, it's 0.01 repeated is equal to 10s, 100s. And subtracting both of these, we get 1 is equal to 99s, and s is equal to 1 over 99. So this number is equal to 1 over 99. So for any repeated decimal, right, we have a general rule now, because we can represent all of them in 0.00. I don't care how many zeros you have, a multiple of something like this, right? If that's a for loop decimal. And so we can probably do something like 0.89 repeated, right? This is just 0.0 and then 89 is repeated. That's equal to 89 over 99, right? Similarly, let's say 0.794. This number would just be equal to 794 over 999, okay? This is just a pattern you can remember, or you can derive it on the spot. You can multiply both. You can let this be s, multiply both sides by 1,000, and then subtract the s's. You get 999 on the bottom, 794 on the top. or you can just remember it. So the general rule also has an extension to some weirder repeated decimals, such as 74.98, where only the 8 is repeated. Now, you might be like, okay, this doesn't fit any of the rules we had just now, right? But notice this thing is just equal to 749.8 repeated divided by 10. And we know what the top is. The top is 749 and 8 over 9. Let me divide this by 10. So that would just be equal to whatever the hell this is. It's just 7049 over 10 plus 8 over 90. And then you can calculate this, right? That will be sort of the number you have, okay? Again, if you're not sure, you can always check back to the materials. I believe that you won't need most of this. Next, we're done with all of these number types. We'll take a look at scientific notation now. Scientific notation is the thing you see on calculators when you have big numbers, the one with the E. Something that looks a bit like this. Okay, and you don't write it like this by hand. You write it with a 10 to the n. So let's say, so this is in old-fashioned calculators, okay? Even in newer calculators, they would just write that as 9.10 times 10 squared. Okay. Let's say we have, a number 480000. If you wanted to express this in scientific notation, you want to write it as an integer, not an integer, a constant, okay? That is no more than 10, okay? And it can't be 10, so it's less than 10. And however, it has to be greater or equal than to 1, okay? So that means it has to be between 1 and 10, this number. So it could be 1.4, right? It could be 1.8. It could be 9.8. All that it can't be is something like 10.2, because that's too big. That's out of the range. So we have a constant, which you can remember as the first digit plus a decimal point. Okay, so the first digit plus a decimal point after that. So a first digit plus the decimal point after that, and then everything behind. So for this number, you would have 4.8 as your constant C, because it's between 1 and 10, right? And then the rest, you just count how many places there are. So if you have 1 place, 2 place, 3 place, 4 place, 5 place, 6 place, that will be 6 tens. You're multiplying 6 extra tens on top of 4.8. You're multiplying 6 extra tens on top of 4.8. And that's how you write numbers into scientific notation. Comparing numbers in scientific notation should be trivial if you are one of the people watching this. I believe it can't be too hard for you. Let's say we have 4.8 times 10 to the power 6 and 7.9 times 10 to the power 6. Obviously, the bottom one is bigger, right? And then if you have 1.2 times 10 to the power 6 and 3.4 times 10 to the power 5, obviously the one on the top is bigger. Why? Because it has 10 to the power 6, right? So it has more digits than the bottom one. So this means the first digit is bigger, so the number is bigger. This means the number of digits is bigger, so it's a bigger number. Okay, that should be trivial. Don't want to talk too much about that one. Now we can talk about ratios. So ratios are sort of a comparison of one number and another. Let's say we have 10 apples, okay, and 30 oranges. The ratio of these two numbers would be, we express ratios as columns, right? So that would be 10 to 30. And a ratio of 10 to 30 simplifies down to 1 to 3. Notice how dividing 10 on both sides doesn't make a difference. Why? Because we're looking at the relative size, right? The relative size of this is triple of this, right? Similarly, if we had, say, 15 apples and 25 oranges. The relative size comparison of these two is 3 to 5, right? And it doesn't matter how big the numbers actually are. It's just sort of the relative size that we're looking at. Hence, we can divide by numbers. And notice that 3 to 5 is actually identical ratio to 1.5 to 2.5. We just like to write ratios in integers because it looks better. So remember to always express your ratios as integers. If you're expressing a ratio as a fraction, the number that you're comparing with always goes on the top. The number you're using to compare always goes on the top. So that would be 3 over 5. Why? Because this means this means we're looking at 3, right? And when you're multiplying by a ratio, you're using this as a subject, and you're doing a manipulation on it to make it the number you want. So let's say you have 3 to 5 apples, right? 3 to 5 apples to pears. Apples to oranges. Let's keep it that way. And what this ratio is basically telling you is, knowing the number of oranges, you can find the number of apples. Okay? I know it's a bit confusing. It's written the other way around. It's saying, knowing the number of oranges, you can find the number of apples. And the reason why we write this fraction like this is because conveniently, the apples is equal to this fractional ratio multiplied by the number of oranges. And the ratio is basically allowing us to find the number of apples given the number of oranges. So this is how you would write the ratio in fractions, okay? 3 over 5. Now, that's just the very basic things of ratios. So far we have covered number types, scientific notation, ratios. Proportions identical to ratios. I don't want to talk too much about that. We will talk a bit about that in trig. And then let's take a look at percentages. Right? Percentages should be simple. I do not expect them to be hard for most of you. I think the harder topics are coming later. Let's say we have a number 0.8, right? To turn that into a percentage, remember that a percentage is just a number over 100, and we can add a percent sign to the number on the top because it's per 100. So you always multiply by 100 over 100. Okay, don't multiply by 100. So a lot of people make this really stupid beginner mistake that I see, and they do this. And yes, the number you get is right, but the both sides are actually not equal. On the left side, you have 80. On the right side, you have 80%. These two numbers are not equal. 80% is way smaller than 80, right? 80 times is like making it bigger, and 80% is making it smaller. So these numbers are definitely not identical. So you should never write like that. Instead, you should write multiply by 100 over 100, because that's 1. And this allows you to get 80 over 100, which you can then say is 80%. And the reason why it's called percent is because cent, if you study Latin, hi Terry, if you study Latin, cent means 100. Okay, century, cent, what else do we have? Centipede just means 100. And so percent means out of 100. You want to make a fraction with 100 on the bottom to be able to convert it to a percent. And the percentages of a number is even simpler than that, right? Like I just showed you, a percentage is, in theory, just a fraction. So we have 400 bits, right? 400 thingies. And you say, I take 80% of this, right? And then most people just multiply 80, divide 100. That's not what a percent means, right? Think about what a percent means. A percent literally just means out of 100 pieces. So every 100 pieces, you get 80, okay? And so 80% of 400 is every 100 of the 400, you get 80. So you can multiply that by 80 over 100, and that gives you 320. So that is how you use percentages. And similarly, if we say 80% of an object is 400, okay? That's a little bit different, but you can, again, express this normally using math. Don't overthink it. Don't memorize it, right? 80% of Q is 400. So we can say 80 bits out of 100 of Q is equal to 400. And then you can divide this fraction onto the other side. So Q is equal to 400 multiplied by 100 over 80. And that's how you use the percent. You can memorize it. You can say if 80% of Q is 400, then Q is 400 divided by 80%. Yes, you can do that. But you can also manipulate the expression so that it's much more intuitive and much more easier to understand. And so that's it for percentages. We'll take a look at interest now, right? So there's two different types of interest. You have simple, which looks a bit like a linear graph. Nice. And we have the compound interest, which looks like an exponential graph, which we will learn about in grade 9. Okay, looks a bit like that. And so you have your simple interest, your compound interest. And what is a simple interest and what is a compound interest, right? A simple interest is that you're only adding from your initial value. You have an initial deposit of $100. Every time the bank gives you 1% of your initial deposit, it gives you $1. the first year. It gives you one more the second year. It gives you one more the third year. It doesn't matter how much money you have in your bank, okay? Let's say you have $300 in your bank. They don't care. They only care that you put $100 in first, and they're just going to keep adding one. And that's simple interest, okay? And a year is over-exaggeration, but a lot of sort of questions will use banks that use simple interest by the month. And compound interest is, well, by the name of the thing, it's compounding. You have 100 the first year, you get 101, and then, because that's 1%, right? And the next year you get 1% of that. So you get 101.01. I mean 102.01 because you're adding 1.01, right? That's 1% of your current deposit. And that actually compounds over time. So it's adding more and more every time. So it's faster, technically, than simple interest. And you might be like, what's the formulas for these then? Again, it's just intuition. You have K in the start. That's your initial deposit. That's your savings. That's your whatever you call it. I forgot what you call it. It's base cash or something. That's how much you start with. And then you add how much interest you have every time, multiplied by how many times you've added that interest. So you have, again, I don't remember the constants for these. What is it again? God. Let's take a look. Oh, that is weird. Ignore this for a second. Where's my Safari? Okay, Chrome. Let's see. Please don't be my brother's random crap. What the hell? Why is he doing this? What is this? What is this? Okay. Getting distracted. The formula is literally just the space, the base money you put in, plus how much time it's going through, plus sort of the interest. What do you call it? The interest percentage. So it's this, right? Oh, so it's P and RT. Okay, cool. Rate. What's the first one called? Principal. Right, principal. Okay, we'll use P then, since that's a standard. Okay, P is the sort of principal. The oh my God, why is it even called principal? The principal money you put in, right? And then you have the rate and the time. And you might be like, okay, this looks completely different from what you were describing just now, right? But this is actually just P, which is how much you're adding. You can expand the brackets, right? This is how much you have in the start, plus how much you get every year, which is how much you have in the start, multiplied by how much percent of how much you have in the start they're giving you, multiplied by how many times they're giving that to you. This is identical to this. So this is the formula we have, right? The sort of total that you end up with is P times 1 plus RT, okay? Remember, this is not how much interest they're giving you. This section is how much interest they're giving you. This thing is how much you're ending up with, the entire balance, okay? And then for a sort of compound interest formula, you still have indeed a principal, but every year on top of that principal, you keep that principal, but they're adding a rate, right? The rate. However, the rate is not based off the initial principal. It's based off how much time you're going through. So it looks like this. And why is it exponential, right? Why is there this weird t exponent? Well, let's say you have $100. The first year, you have 100 times 1 plus the rate that they're giving you, right? The next year, you have this much. And then, on top of that, you're getting that initial money plus the rate the bank is giving you. And then the year after, it's this. That's why we have this t exponent here, okay? Nice, so that's the first two units covered. We have number types. We have ratios and proportions and percentages. And now we're going to look at our, not really latest unit, but the latest important unit, which is algebra. So, quadratics, right? Really simple. I think this should be fresh in your minds, so I'm not going to show too much about it, okay? Remember, any quadratic you can factorize it, and if you factorize it into the form x minus a times x minus b equals 0, then the solutions are either x equals a or x equals b. And the way you can find this factorization is there's a lot of different ways. There's a cross way. Let's say we have x squared plus plus 2x minus 8, okay? And if you have this number, then what a lot of people do with their thingy is they do this, and they say, hey, there's a negative 2 there, there's a 4 there, and so this thing is 1 times 1, this thing is 4 times negative 2, this middle thing is 1 times 4 and 1 times negative 2, and that's a smart method, right? You can use that to check. But you might be thinking, okay, we've learned this is okay-ish useful. How do I actually find the factors? And that's a great question, so I'll explain that to you now. There's actually a few ways that people like me who do math in competitive ways find the factors. First of all is to just try every single one out in your head, right? You have a 6, you think about 2 3s, you think about 1 6, you can think about negative 2, negative 3, right? You can think about negative 1, negative 6. This is honestly the fastest way. If you want to do it in a more interesting way, there's something called the factor theorem. And I encourage you to search that up. It's outside of the curriculum we've learned, so you can skip that if you're just trying to revise everything we've learned. But if you want something useful to help you factor quadratics, the factor theorem is a go-to. Let's say we have x squared plus, let's do something harder, right? Let's do x squared plus 7x plus 12. Let's say you want to factor this. Now, there's a very interesting thing called the factor theorem that states if let's do minus 12 actually, because that will be easier to show. If substituting a number q allows us to make this expression equal to 0, then x minus q is a factor. What does this mean, right? You might be like, that's a really confusing statement. So let's get rid of this first. What? This is not getting rid of itself. There we go. Okay. Okay. Basically, for this equation, right? Let's first try something. Let's substitute q is equal to 3, right? What is 3 squared minus 7 times 3 plus 12 equal to? That's 9 minus 21 plus 12. That's equal to 0. Cool. Substituting x equals 3 makes this 0. What does that mean? According to the factor theorem, that means one of the factors of this quadratic is actually x minus 3. And that's actually really useful, because now you know what the other one is because of the constant term. You know the other one has to be x minus 4. And you just factor the quadratic without trying the actual numbers. You just tried substituting this thing in there. Just remember that if the number you substitute in is a negative number, then it becomes x plus that number, right? Because let's say substituting negative 2 makes it work. Then the factor would be x plus 2. Okay, just remember that. That's about it for quadratics. We haven't talked about plotting quadratics yet. Well, so that might be for next year. What else have we talked about? We have talked about, let me think. We've talked about factoring quadratics. We've talked about some really basic stuff, haven't we? Let's say we have x minus 2 squared equals to 4, right? You can square root both sides. That has to be plus minus 2. Right? You move this over, x equals 2 plus minus 2. Okay, remember, just remember when you're square rooting both sides, you have to add the plus minus. I think that is surprisingly about it for quadratics. Next, we have our very basic algebraic substitution. Shouldn't be hard. Let's say we have a number like, show q in terms of this, right? This shouldn't be hard. 4q, why does that sound like for q? 4q is equal to, you can move this over, that's equal to x minus 9k, right? And then you have q is equal to x minus 9k over 4, right? This shouldn't be hard. You just want to keep that variable on one side, move everything over to the other side, and then get rid of the coefficient of that number, right? So let's say Another one. 7 equals x over k over x plus like 8p or something like that. And then it wants you to find x, for example, right? You want to first get rid of everything, so you can move this over, right? You have 7 minus 8p is equal to k over x. Right, and then you can flip both sides. Remember, this is called taking the reciprocal. You can take both sides. You can flip both sides. You can x over k equals to 1 over 7 8 minus 8p. And then you can multiply both sides by k. So k over 7 minus 8p is equal to x. Remember to always check for weird cases. Like in this case, you need to write x is not 0. Okay? Because fractions can't have 0 in the denominator. Now, that's it for algebra. Trig. The love of my life. Trig. Okay. Trig is all about triangles. The essential idea of trig is based on something called similarity. And similarity states that, well, when you scale a triangle up, the side ratios don't change. So let's say the small triangle has sides A to B to C. The bigger triangle, if you scale it up, right? Let's say you scaled this triangle. Ooh, it's so big. Yeah, it's big. Just like and then the next triangle becomes A prime, B prime, and C prime. Then, according to AA similarity, which means if you have two angles that are equal in these two triangles, we have A over A prime is actually equal to B over B prime equals to C over C prime. This is called the scale factor. And trig is all about the scale factor. Why? Because if A over A prime equals B over B prime, right, after we scale these side lengths up, this actually gives us, if you divide this by this and divide this by this, right, you can rearrange it. You can multiply both sides by AB prime. You can multiply both sides by B prime first. You get AB prime, not factorial. AB prime equals to BA prime. And then you can divide both sides by B prime A prime to get A over A prime equals B over B prime. And this is our so-called trig ratio. Wrong thing. What am I dividing? You can divide both sides by, my fault. You can divide both sides by BB prime, so you can get A over B is equal to A prime over B prime. And this is the trig ratio we were talking about. A over B equals A prime over B prime. So that means for a triangle, if you scale it up, scale it down, whatever the hell you do to it, okay? The ratios between the sides themselves don't actually change, which is why this random guy thought of trigonometry. Because if you have a right angle and the other angle stays equal, the triangle is just a scaled up version of it, right? Because two angles, remember, AA similarity, you'll learn this in grade 10 or grade 9. If two angles of two triangles are same, one is just a scaled up version of the other. So this triangle is just a scaled up version of this guy. And so this guy thinks of trig and he says, let's say this is A, this is B, and this is C. And then we can set these cool little ratios that will never change if the angle stays fixed. So we have A over C is defined as sine, B over C is defined as cosine, and A over B is defined as tangent. And this is memorized using the mnemonic SOHCAHTOA, S, opposite over hypotenuse, C, adjacent over hypotenuse, and T, opposite over adjacent. So SOHCAHTOA. What I remember is sine is more important than cosine. And so tangent is just sine divided by cosine. Okay? And sine divided by cosine is actually, if you cancel out some of the fraction parts, that's literally just what tangent is. Okay? Now, if we have all of these things, we can actually think of a few different things about our triangles, which again, I'll talk about right now. Let's say we know this side. We know this angle, right? Let's say this angle is alpha. Let's say we know the side as 4. This side and this side, we know a ratio, right? So if we want to find the hypotenuse, we can actually say 4 divided by the hypotenuse is equal to sine of alpha, right? We know this. This is by definition of trig. And then we can then find h by multiplying h over to the side. We have h sine alpha, and we have 4 on this side. And then we can divide this over, and we have h equals sine alpha over 4. And that's how we can find side lengths using trig, right? Again, I won't go over this in too much detail. You can look at my other stuff on this, or just look back at the teacher slides. That's how you can find a side length based off the angles and sides in a triangle. We call this solving a triangle. Similarly, you can find an angle, right? If you know these two sides. Say we know 4 and 8, we know this angle. We don't know this angle. We want to find this angle. right? Let's say this angle is alpha, okay? Let's let this angle be alpha. Remember, in this case, alpha is a known variable. We know the alpha. Let's say this is just 30, right? I was trying not to think of a random number, but, we can express h in terms of the angle and the side, right? Here, we don't know the angle. We can express the angle in terms of the side. In here, we have sine alpha. We know sine of alpha is equal to 4 over 8 from the diagram, right? By definition, 4 over 8 is sine of alpha. We can then do something called taking the inverse, okay? And I'll show you this. Sine inverse of this side is equal to sine inverse of this side. It's called arcsine. So we can take this in both sides, and the sine inverse and the sine actually cancels out, leaving with us alpha equals sine inverse of 4 over 8. And I'll show you why this works in a moment. Essentially, we call sine a function, okay? And we call this the domain. This you will learn in grade 12. This is the domain and this is the range of a function. Sine projects this group called the angle group. Okay, we called it the angle set. Onto this ratio group. So sine says, you know the angle, you get the ratio. That is so cool. And then, what does inverse sine do? Inverse sine says, you know the ratio, I'll give you the angle. And that's what inverse sine does. So these two are called inverse functions, and basically it means one of them reverses what the other one did. So if you signed and then inverse signed, you're back to where you were. Which is why in this place we can take sine inverse of both sides. Just now, that was what this was. Why can we take the sine inverse of both sides? Because these two guys cancel out. You revert back to where you were in the beginning. So that's all we really need to know for trig. I'm not going to teach the law of sines and law of cosines here. You can, again, read through my other stuff there. Those are things that are way more complicated than we really need. But again, the really annoying question that looked like this required the law of cosines, which took me half an hour to work on. But again, right? So that is a separate topic that you can research yourself. And I don't believe that will be needed for the test. And then finally, we're on to coordinate geometry. We just had this test recently, so I'm not going to cover it. Just remember a line has 3 forms, general form ax plus by plus cz equals 0. No CZ. Oh my god, I got confused with my APMO stuff today. AX plus BY equals C. That's a standard form. The slope-intercept form MX plus B. And finally, the, the point-slope form, which is M of x1 minus x2. x1 minus x2 equals y1 minus y2, right? And I think that's about it. I just hope, let me see if I did. God, I hope I recorded this with audio. Yes, I recorded this with audio. Let's freaking go. So that's it of the video. See y'all next time. I just wasted half an hour on nothing. I have math to do. I have physics to do. And I'm out of here. Thank y'all. Bye.